And we're now recording. So recording is underway. And let me go back to sharing the screen. All right, so we're down to just the last section of the chapter. So 15.9, I was going to do that today. Okay, again, these problems could get really, really long if you wanted to. Okay, I'll try to make it as painless as possible. Well, the first few problems are very straightforward. They're only just finding the Jacobian. That's no big deal. But to do a problem from beginning to end really takes a long time. Right, and then I can probably get started with some of 16.1, our last chapter of Calc 3. So again, calendar-wise, this is the game plan. So we are here. Yeah, I just got a message that says my internet connection is unstable. You ever get that message? So if I get disconnected, hang in there. I'm going to try to get back on. That's happened before. But hope not. All right, so 15.9 and then hopefully 16.1. 16.1 is not that long a section at all. I think I can get all this done. Okay, so again, we're aiming for exam 4 to be Thursday, the 22nd, a week from Thursday. I will go on with 16.1, 16.2 and whatnot. Okay, so let's say the second half of, whoops, screen is starting to freak out a little bit. Okay, so don't be surprised if I get disconnected, but I'll try to get back in. But that's the way it is when we're teaching virtually, right? So let's see. Yeah, Tuesday the 20th, second hour, I will let you have for questions and answers if there are any. Okay, and just like the previous exam, on the 22nd, we'll go straight to the exam. Some of the problems take a long time, so you can have the entire time, no question and answer, no new material, just the whole time for the exam. Okay, and same plan for exam 5. Let's plan that being Thursday the 13th of May. I'm not sure about all these dates, but if I can land it right here, then Tuesday the 18th will be a question and answer session, and then final exam on the 20th. Is that right? Okay, so that's what we're up against. All right, so 15.9, I introduced some of it last time, so the introduction last time would just make things a little bit easier for me for today before I get started with doing the homework problems. Okay, so let's review what's happening. 15.9, page 1052, change of variables in multiple integrals. Okay, so remember last time we were talking about the U substitution, right? So when we integrate in Calc 1 and Calc 2, it was a line segment to another line segment, right? So if you integrate from 3 to 10, maybe by doing the U substitution, the new integral goes from 25 to 75 or something like that, right? That was possible. Okay, so something similar is going to happen when you have multivariable, only it's much more complicated potentially. Okay, now if you're in one dimension, stop and think about it. You have a line segment. You're going from A to B. Okay, then when you change it to a new variable, it's still a number line. So you have a different line segment perhaps that still goes from C to D. But in 2 space, okay, you could see the UV plane and the XY plane that they have. You might go from one to the other. You could have a completely different region. Okay, so depending if you're doing, they call it transformation T, which is a function, essentially UV going to XY, or vice versa, T inverse. Okay, XY going to UV. So you have the XY plane, you could go to the UV plane and vice versa. And by doing that transformation, you could have a completely different object. Okay. So again, it's much more rich in possibilities, as we said. Figure 2, we said here, okay. So you could have a square region being mapped over to this funny thing, okay, where the transformation is given by this. Okay, so you know how we have just a single variable, right? U equals, I don't know, 3x squared minus 5x plus 6 in Calc 1 and 2. Right? Now you have x and y as functions of u and v, or vice versa. So you might have a, let's say, a square region going to this funny thing. Okay, and again, this is helpful, and you'll be doing a lot of this in our last chapter, chapter 16. But see the one, you can see that one line, 1 arrow, 2 arrows, 3 arrows, 4 arrows in orange, becoming the 1 arrow, 2 arrows, 3 arrows, 4 arrows in the XY plane. right? So you can have something completely different. All right, so I'm just letting you know ahead of time, the quiz on Thursday that I'm going to give you is going to be something like that. Okay, but I won't make it too tough. It'll be something that you should be able to figure out fairly reasonably. All right, so when you make the transformation, you know how you have u equals blah, 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 du equals something dx. That something in multiple variables is the Jacobian, the multiplication factor. Okay, so when you go from change x to u, you can't just change du to dx. There's a multiplication factor, right? So like something simple, u equals x cubed, du equals 3x squared dx. That 3x squared is now what we're calling the Jacobian. It's an extra multiplication factor. All right. And what does it say? Oh, your internet connection is unstable. It says it again. All right, well, we'll see what happens. All right, so the extra multiplication factor, the derivation is there. You can look at it or not, but it basically comes from a cross product of r sub u cross r sub v. Okay, and we get something called the Jacobian. Okay, so you want to put this on your next cheat sheet for the Jacobian. You don't need all this, but this here. Okay, and where is it? Page 1055. The Jacobian, where it's given x as a function of u and v, y is a function of u and v. It looks like the partial of x y with respect to uv is take everything on top, take the derivative of everything on the bottom. So partial of x with respect to u and v on the top, and then on the bottom, partial of y with respect to u and v. And it's a usual 2 by 2 determinant, right? So that times that minus that times that. Okay. The three-dimensional Jacobian, put that on your cheat sheet. Page 1059. Number 12. Partial of x, y, z with respect to u, v, w. So you take the derivative of x with respect to u, v, and w, top line. The partial of y with respect to u, v, w, middle line. And the partial of z with respect to u, v, and w, bottom line. And you evaluate this 3 by 3 determinant the same way as we did earlier 3 by 3 determinants. Okay. And then to actually do a double integral, page 1056, here's the formula. I didn't give you that many. It can get really long. All right, so double integral over the region R of f of x, y, dA. dA is in the xy plane, equals double integral of a new region S. Okay, f of x of uv, y of uv. So in other words, change x and y to u and v. Okay, so dA, which is dx dy, becomes du dv, but you have to multiply by that Jacobian, that extra multiplication factor, absolute value of the Jacobian. Okay, so partial of xy with respect to uv. Okay, so that's like when you said u equals 3x squared, du equals 6x dx. That 6x is like the Jacobian. So we have that. Okay. In 3 dimensions, I'll show it to you. You really don't have to put this in your cheat sheet because it just gets too long. But just what you would do in 3 variables on page 1059, just by analogy. Okay, but I will not give you anything that bad. It's really, really long. Okay, so f of x, y, z, dv. You have a region in space, that R by 13, 3-dimensional region. It becomes a new 3-dimensional region, possibly called S, after you change x, y, z to u, v, w, times the absolute value of the Jacobian, du, dv, dw in some order. Okay. All right, I'll just mention this in passing. You don't have to write this down. But if you have x, y, z, and you change it to rho, theta, and phi, so I'll just say it, you don't have to take notes. But see, those are the formulas for spherical coordinates, right? X equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi. They actually computed the 3-dimensional Jacobian, partial of x, y, z with respect to rho, theta, and phi. So this is the partial of x with respect to rho, theta, and phi. You can do it as well as I can, right? This is the partial of y with respect to rho, theta, and phi. And this is the partial of z with respect to rho, theta, and phi. And they computed all of that, and the Jacobian comes out to be negative rho squared sine phi. Okay, the absolute value, of course, is positive rho squared sine phi. And so that does make sense, right? So when you change dv from dz, dy, dx to rho, theta, and phi, that's why you have to multiply by, now we know it's the absolute value of the Jacobian, rho squared sine phi. So that's why in spherical coordinates, you have to change dz, dy, dx to rho squared sine phi, that multiplication factor, times d rho, d theta, d phi, because the Jacobian came out to be negative rho squared sine phi, whose absolute value is rho squared sine phi. Okay. And yes, something similar happens in the cylindrical coordinates. Okay, as you might guess, the Jacobian comes out to be r. The extra multiplication factor was r, right, in both polar coordinates and cylindrical coordinates. All right, but enough of that. Let's get to work. Okay, so 15.9, we quote unquote only have to do 1 to 17 odd and skip 11. Okay. So let me show that to you for those of you that don't have the book and aren't getting it. Okay, first problem is find a Jacobian, no big deal. Find the image set, that is a big deal. Okay, and then a few full-fledged integrals, okay, which can get really, really long. Okay. Right. Okay, finding a Jacobian should not be that big a deal. All right, so number one, x equals 2u plus v, y equals 4u minus v. So the Jacobian, I will abbreviate Jacobian with a capital J. Kind of makes sense. So by formula, the partial of x, y with respect to uv. Take everything on top, differentiate everything on the bottom. So it's the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Very straightforward. Okay, so partial of x with respect to u, 2. Partial of x with respect to v, 1. Partial of y with respect to u, 4. Partial of y with respect to v, negative 1. Okay, then I figure out the Jacobian. I have to watch out. Okay, this is not absolute value. This is evaluating a 2 by 2 determinant. So it's just that times that minus that times that. So negative 2 minus 4, negative 6. Okay, so that's pretty straightforward. Okay, then I'll do one of the 3-dimensional Jacobians. Number 5. X equals uv, y equals vw, z equals wu. So a little bit harder, but still hopefully not too bad. Partial of x, y, z with respect to uvw. So on top is a partial of x with respect to uvw. Middle one, partial of y with respect to uvw. And then partial of z with respect to uvw. Okay, partial of x with respect to u, v. Partial of x with respect to v is u. Partial of x with respect to w, there is no w, so 0. Okay, and then y equals vw. Derivative with respect to u, there is no u, that's all constant, so 0. Partial of y with respect to v, w. Partial of y with respect to w, v. And finally, z is wu. Partial with respect to u is w. Partial with respect to v, there is no v, so this whole thing is constant, therefore its derivative is 0. And the partial with respect to w is u. So there we go. All right, so we know how a 3 by 3 determinant goes. It's v times a 2 by 2 minus u times a 2 by 2 plus 0 times a 2 by 2 But of course, 0 times anything is 0, so forget about it, right? And by the way, when you do this for me on a quiz, homework test, you should do exactly as I do. So you could do a Jacobian without doing this, but I want you to do this. I want you to know how to do a determinant. So you should show me all this. In summary, it's always a good idea. If you say, how should I do it? Do it the way the teacher does it, right? All right, so V times WVU, 0U, right? Remember, put V and then eliminate V's row and column, WV 0U. Then remember this one is a minus U. Minus U, block out U's row and column. I see 0VWU plus 0 times something. And say, wait a minute, 0 times, we don't care. Forget about it, right? All right, so it's V times UW minus nothing, minus U times nothing minus VW, and that's nothing. So I have UVW minus a minus a plus another UVW. Final answer is UVW. All right, so that's all there is to Jacobians. Now for fun stuff. Find the image of the set under the given transformation. Okay. These can get really long. Mr. Stewart actually was very nice, gave us fairly reasonable ones, and there was only 4, of which 2 are odd, and I'm probably going to end up just doing them both anyway. But it can get really, really bad, as you might guess. All right, so here you're in the UV plane. U is going from 0 to 3. V is going from U to 2. What happens in the XY plane? And X is 2U plus 3V. Y is U minus V. Okay, now it could go the other way also. In other words, you could start off in the XY plane and then give you a transformation in the UV plane. So you have to be ready to go both ways, whatever they give me. So here's what we got. So here's the picture. This is the UV plane. Okay, so they said, I broke it up into L1, L2, L3, L4. Okay, V is going from 0 to 2, U is going from 0 to 3. Okay, and in case you're wondering the convention, U is before V in the alphabet, right? So U is functioning like X, V is functioning like Y. So UV like XY, right? And here's the transformation. X equals 2U plus 3V, Y equals U minus V. That was given. Okay. That's just like in one dimension. So I want to do a U substitution. U equals, I don't know, sine X minus cosine X or something like that, right? But now you have 2 variables, 2 variables. Okay. This is going to be a linear transformation as it turns out. Okay. This is linear. This is linear. So it's going to be a linear transformation. In other words, we don't have to worry about curve stuff. It's not going to be a sine function, a parabola, or whatever. Okay. All right, so here's what I do. I broke this up into 4 line segments: L1, L2, L3, and L4. Okay. L1, V equals 0. L2, U equals 3. L3, V equals 2. L4, U equals 0. And we're going to say, what happens in the XY plane? All right, so first, let's just see what happens to the corresponding points just by plugging. Okay. And now, so that you don't get mixed up, you have to put down whether in a UV plane or the XY plane. So you can write UV like this, or you could also just write UV like so and XY like so. So where does 0, 0 go in XY? Okay, so plug in U is 0, V is 0. That's easy. Put 0, 0, X is 0, 0, 0, Y is 0. So 0, 0 stays the same. How about 3, 0 in a UV plane? Okay, so plug in. X is, U is 3, V is 0. Put a 3 there, a 0 there. 2 times 3 is 6 plus nothing. So X is 6. What happens to Y? So Y is U minus V. 3 minus 0 is 3. So the point 3, 0 becomes the point 6, 3. Okay. How about this point? 3, 2. So I plug in 3, 2. Put a 3 there and a 2 there. 2 times 3 is 6. 3 times 2 is 6. 6 plus 6 is 12. So x is 12. Y is u minus v. So 3 minus 2 is 1. So the point 3, 2 becomes the point 12, 1. And finally, 0, 2 in the UV plane. Okay, so this is UV, this is XY. So 0, 2. Plug in 0 here and 2 here. That's 0 plus 6, so that's 6. 0, that's a 2. 0, 2. 0 minus 2 is negative 2. So 0, 2 becomes 6, negative 2. Okay, so you get a weird shape. This nice rectangular region becomes 0, 0, 6, 3, 12, 1, and 6, negative 2. And yes, it does come out to be a quadrilateral, which I will prove right now. That can get really long. We are going to actually have to do some of this in our last chapter, chapter 16. Okay. Now, for the quiz I'm going to give you on Thursday, I'll just have you find these corresponding points, and then you can graph it. But we basically have a quadrilateral determined by 0, 0, 6, 3, 12, 1, and 6, negative 2. Now, how do you know it's going to be straight line, linear? Well, this is the proof of that, and that can get long. But here we go. So here's what we do. So L1, V is equal to 0, right? Line 1, L1, V equals 0. So I plug in V equals 0 there. I get x equals 2u, right? Put v equals 0 there. I have y equals u. So x equals 2u, y equals u. Since y and u are equal, I put that there. So I have x equals 2y or y equals half x. So in the xy plane, this thing becomes y equals a half x. That has a slope of a half. If you stop and think about it, that makes sense because let's see, I'm going from 0, 0 to 6, 3. So the slope is a half. But I am going in a straight line fashion. Okay, L2, u equals 3. That's this, right? All right, u equals 3. Put a 3 right there and a 3 right there. So put a 3 right here, right? 6 plus 3v. X equals 6 plus 3v. U equals 3. Put a 3 right there. Y equals 3 minus v. A little bit of algebra shows you that v, put the v there and y there, v is 3 minus y. Okay, so now I pick this up and plug it right here, right? X is 6 plus 3 times v, 3 minus y. X equals 6 plus 3 times 3 minus y. Okay, you could make that work out as y equals mx plus v, but the main thing is that it's linear. I want to show you that it's linear. It's a straight line. So we're not going in a curve. So we're going in a straight line fashion from 6, 3 to 12, 1. Okay, L3. L3, V equals 2. Okay, so V equals 2, put a 2 right there and a 2 right there, right? If I put a 2 right there, X is 2u plus 6. We said V equals 2. Put a 2 right there, Y equals u minus 2. Which means u equals, let's see, 2 plus y. Agree? Okay, pick this up and plug it right over here. 2u, 2 parentheses, 2 plus y plus 6. Again, you could make it look like y equals mx plus b. That's linear. So indeed, I do have a straight line segment. And this time that would have been what? 12, 1 to 6, negative 2. And finally, I call it L4, u equals 0. That's a little bit easier. Okay, plug in u equals 0. So that's 0. X equals 3v, right? Put a 0 there. Y equals negative v. Okay, so x equals 3v, y equals negative v. Solve for v. V equals negative y. Plug that right over here. X equals negative 3y. That's linear. Y equals what? Negative 1/3 x. All right, so all of that was to show you, okay, I am going in the xy plane from 0, 0 to 6, 3 to 12, 1 to 6, negative 2, and they're all linear. Okay, the quiz I'm going to give you on Thursday, it'll be linear. Okay, so you won't really have to go through all this analysis unless you felt like it. Okay, you'll basically just be plugging in endpoints. Okay, so the transformed shape is a quadrilateral determined by 0, 0, 6, 3, 12, 1, and 6, negative 2. Okay, so I will draw very crudely because it takes too long to draw it exactly. Let me see if I can do this. Zero, 0, 6, 3, maybe it's like there. 12, 1 is way over here. 6, negative 2 is like this. So that, 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 and that. Okay, and in the order. So I'll do my arrow thing. So 1 arrow, 2 arrows, 3 arrows, 4 arrows. 1 arrow, 2 arrow, 3, 4 arrows. Became 0, 0, went to 6, 3. So 1 arrow, 2 arrows, 3 arrows, 4 arrows. Okay, so here's 0, 0. It went to 6, 3, which goes to 12, 1, which goes to 6, negative 2, and then back home. Okay. And the other interesting thing is, looks like the original was counterclockwise, right? But by doing this, I'm now going clockwise. So again, here's another thing, you know, it's very rich and complicated. So now you're going back to Calc 1, you're going from one interval to another interval. You know, is that all? Right? Remember doing U substitutions in Calc 1 and Calc 2, right? You integrated from A to B, then after you transform, right? U equals blah, blah, you integrated from C to D, one interval to another interval, right? So the original interval, let's say, was from 3 to 10. The new interval goes from 5 to 21. It was a line segment to another line segment. Now you can see how rich the variety is. This rectangular region gets transformed into this quadrilateral region. I don't even know for sure if it's a parallelogram or whatever. But so if you make that transformation, this rectangular region becomes this region. Okay. All right. So here was UV changing to XY. You might have to go the other way also. You might have XY going to UV. In fact, normally when you have a basic integral problem, you start off with XY, right? And then you change the UV. So you might have to go the other way too. Okay, so as far as the quiz on Thursday is concerned, I'll give you something just like this, okay, where you have a region and I want you to give me the transform region. Okay, but it'll be linear, which means you don't have to do all this rigmarole here. Okay, you can basically just figure out the endpoints and then draw what the new picture will be. So that makes it much easier. Okay, number 9. S is a triangular region with vertices 0, 0, 1, 1, 0, 1. X equals U squared, Y equals V. Okay, so you're starting in the UV plane. What happens in the XY plane? And to me, this was kind of bad because they're going from UV to XY. I think they should have gone the other way, XY to UV, because that's normally what happens, right? Our integrals would normally start off with XY, then you would change them to UV, but be that as it may. All right, so it says you have a triangular region bounded by 0, 0, 1, 1, and 0, 1 in the UV plane. Okay, that's easy. This is U equals V. I think of Y equals X, right? V equals 1. I think Y equals 1. Okay, so in my mind, U, V is X, Y. So U is like X, V is like Y. Okay, so here's U equals 0, V equals 1. Okay, now let's see where the points go to. Okay, where does 0, 0 in the UV plane go to? So plug in 0, 0. I'm still at 0, 0 in the XY plane. How about in the UV plane 1, 1? So U is 1, V is 1. 1, 1. It's still 1, 1 in the XY plane, right? How about 0, 1 in the UV plane? Put a 0 here and a 1 here, 0, 1. So all 3 points stay the same. 0, 0 stays 0, 0. 1, 1 stays 1, 1. 0, 1 stays 0, 1. So, hey, I still have a triangle. Well, let's try it. Okay, so I broke it up into L1, L2, and L3 just like last time. Okay, so L1, U equals V. L2, V equals 1. L3, U equals 0. All right, so L1, U equals V. Right, so if U equals V, then X equals V squared, right? If they're equal. X equals V squared, Y equals V. Well, if Y and V are equal, I can put a Y there, X equals Y squared, or Y equals radical X. Y equals radical X looks like that. So even though I'm still going from 0, 0 to 1, 1, the straight line got transformed into the parabola. Okay, L2, V equals 1. If I plug in V equals 1, well, it says Y equals 1, and U just goes from 0 to 1. So I still have Y equals 1. So that's the same. X equals U squared, U goes from 0 to 1, X goes from 0 to 1. So that's the same thing. And then L3, U equals 0. If I plug in U equals 0, X equals 0. So that's the same. And Y equals V. So Y still goes from 0 to 1. So that's the same. So here is my transformed region. Looks like this. And I'll do my arrow thing again. So 1 arrow, 2 arrows, 3 arrows, 1 arrow, 2 arrows, 3 arrows. Okay, so this straight line here, 1 arrow, became the curve. And the other 2 stayed the same. Okay, so the 2 arrows there becomes the 2 arrows there. The 3 arrows there becomes the 3 arrows there. So just because the endpoints are all the same, doesn't mean you have the same graph, right? The triangular region became this region. Again, please notice, we never had anything like that in Calc 1 and Calc 2 even, right? You just had a line segment becoming another line segment. Once you get to multivariable, all kinds of possibilities open up. So now we have this brand new region. Okay. So that is that. Okay, then let's see. What do we have? Number 13. A region R in the XY plane is given. We're skipping 11, so I'm just giving you 13, the only one like that. 11 was too difficult in my opinion. Find equations for the transformation at T that maps a rectangular region S in the UV plane onto R, where the sides of S are parallel to the UV axis. Okay, so what do they mean by that? So R lies between the circles x squared plus y squared equals 1, x squared plus y squared equals 2 in the first quadrant. Well, we know how to do that with polar coordinates, right? X squared plus y squared equals 1, x squared plus y squared equals 2. That's that, that's that. So we know that this is r equals 1, r equals radical 2. All right, and recall we had x equals r cosine theta, y equals r sine theta. Okay. They want us to use u and v. Okay, so I just change it. Okay, x equals r cosine theta, but r is like the u, and theta is like the v. So here are the equations. X equals u cosine v, y equals u sine v. R goes from 1 to radical 2. Sorry, I messed up. Okay, so remember in polar coordinates, x is r cosine theta, y is r sine theta. They told us to use u and v. So there it is. I call that u is r, theta is v. So x equals u cosine v, y equals u sine v. R is between 1 and radical 2. Theta is between 0 and pi over 2. Right? And the nice thing about that, of course, instead of integrating over this funny looking region, I can integrate over a box, a rectangular region, right? R goes from something to something, and theta goes from something to something. Okay. All right, so now for the quote unquote really bad problems. Okay, what time is it? So a full-fledged problem. Use the given transformation to evaluate the integral. So 15 and 17, and they're both two-dimensional. So that means we're just only going to do, we're not going to do this, in other words, too long. We're only going to do this thing. Okay, so we have to find a Jacobian and actually the absolute value of the Jacobian and so forth. Okay. So 15. Double integral over the region R of x minus 3y dA. R is the triangular region with vertices 0, 0, 2, 1, and 1, 2. X equals 2u plus v, y equals u plus 2v. Okay. So let me get this out of the way. All right, now you can see how difficult this integral is, right? This is a triangular region bounded by 0, 0, 1, 2, and 2, 1. So I'm integrating over this region. Not fun, right? But by means of using this transformation, it comes out fairly nice. So let's see. First, we need the Jacobian. So J. So partial of x with respect to u, 2. Partial of x with respect to v, 1. Partial of y with respect to u, 1. Partial of y with respect to v, 2. So that's easy. 2 times 2 is 4, minus 1 times 1, 3. That's the multiplication factor that I need when I finally integrate. Okay. If it came out negative, I would make it positive, right? If it came out to be negative 3, I would still use 3. All right, now the hard part, the transformation. Fortunately, this is linear, right? That's linear, that's linear. It's going to be a linear transformation, so to speak. But I went ahead and showed you everything anyway. Okay, so where does 0, 0 in x and y become in u and v? Okay, so put a 0 here and a 0 here. Okay. You're solving two equations and two unknowns. 2u plus v equals 0, u plus 2v equals 0. It's 0, 0. Okay, that's pretty easy to do. You can figure that out on your own. Okay, but if remember doing two big equations, two unknowns. If this is 0 and this is 0, u and v are both 0. Okay, or maybe think of it this way: you know there's only going to be one solution, and you know 0, 0 works. So there it is. So the origin stays the same. Now it gets harder. Okay, how about 1, 2 in x, y? X is 1, y is 2. X is 1, y is 2. So 1 equals 2u plus v, 2 equals u plus 2v. Okay, 2 equations, 2 unknowns. Okay, so what did I do? I multiplied the second equation by 2. 4 equals 2u plus 4v. And then I subtract it up. I take this equation minus this equation, because that way the 2u's will cancel out, right? So 4 minus 1 is 3. 2u minus 2u is nothing. 4v minus v is 3v. That means v equals 1. And if I plug in v equals 1, let's say right over here, 2 equals u plus 2, u equals 0. So I have the point 0, 1 in the UV plane. So in other words, 1, 2 becomes 0, 1. And now 1, 2 in the XY plane. Oh, I'm sorry, I'm just rehashing what I said. 1, 2 in X and Y is 0, 1 in U and V. And now the last point, 2, 1. Right, so that means X is 2, Y is 1. So X is 2, put a 2 right here, put a 1 right here. Again, 2 equations and 2 unknowns. 2 equals 2u plus v, 1 equals u plus 2v. I played the same trick. The numbers are pretty much identical. Multiply the second equation by 2. 2 equals 2u plus 4v, and then I subtract up. This equation minus this equation. The third equation minus the first. 2 minus 2 is nothing. 2u minus 2u is 0. 4v minus v is 3v. 0 equals 3v, that means v equals 0. Plug in v equals 0, then u equals 1. Okay, so 2, 1 becomes 0, 1. And it's linear. So I don't have to worry about like what happened over here that it became a curve. Okay, so just like the analysis I did for this one, right? It's a linear transformation. So I don't have to worry that it's going in a curve. I can just connect the dots, so to speak. The quiz I'm going to give you on Thursday will be just like that. You just find the new transform points and connect the dots. In summary, look at what happened. 0, 0 in XY, 0, 0 UV. 1, 2, not so convenient, became 0, 1. And 2, 1. See, 2, 1 became 0, 1. 1, 2 became, see, I got this wrong. I should have 1, 0 somewhere here. 1, 2 became 0, 1. 2, 1 became 1, 0, right? 1, 0. All right. In the UV plane, I get this region, which I know how to do. That's pretty straightforward now, right? Compared to this. This triangular region becomes another triangular region, but I know how to do this. Right, so UV plane, I'm integrating over this region. All right, so the original was x minus 3y. X, 2u plus v, plug it in, minus 3 times y, u plus 2v, times the Jacobian, and then du dv. Okay, and this algebra here, 2u minus 3u is a negative u. V minus 6v is a negative 5v. Du dv, take out the 3, take out the minus sign. Now we're home free. Negative 3, integral from 0 to 1. 0 to 1, u plus 5v, du dv. U squared over 2 plus 5uv from 0 to 1. U is 0, plug in 0, you get 0. Plug in 1, you have 1/2 plus 5v dv. So 1/2 v plus 5v squared over 2 from 0 to 1. Plug in 0, you get 0. plug in 1, let's see, you get 1/2 plus 5/2, which is 6/2, that's 3. -3 times 3 is -9. So I have -9. Okay, so you can see there's a lot of work involved in this. Okay, most likely on the exam, I won't have you do this entire problem. That just takes too long. I might have you do just a portion of it. Okay, so it's break time. So after the break, I'll do the last problem, 17, and then I'll get started with 16.1, our last chapter. Okay, so we'll break until our usual about 7:10-ish. Okay. Anybody who joined late, go ahead and tell me in the chat. All right, folks, it's 10 after. We'll go ahead and start. So let's pick up where we left off. And let's see, Andrea, I got you. And Jerry, I got you. So over 10 minutes. All right, so I'm just about done. I was going to do the last problem, 17. So let's go back to sharing the screen. Use given transformation to evaluate the integral. All right, 17, double integral over the region R of x squared dA. R is the region bounded by the ellipse 9x squared plus 4y squared equals 36. X equals 2u, y equals 3v. All right, this one's actually much easier than the previous one. All right, this looks like an ellipse, if you recall, from the earlier analytic geometry. Okay, so have we ever integrated with an elliptical region? Not much. It's not very fun, right? Let's see. Let's see if I can get a rough guess of what this looks like. If I divide by 36, x squared over 4 plus y squared over 9 equals 1. Okay, so its general shape is something like this. So we have to integrate over this region. Not that fun. I cannot switch to polar coordinates because it's not a circle. But let's see what happens if I do this transformation. X equals 2u, y equals 3v. So I need a Jacobian. Partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Partial of x with respect to u, 2. Partial of x with respect to v, there is no v, so 0. Partial of y with respect to u, there is no u, 0. Partial of y with respect to v, 3. Right? So that's 6 minus nothing, or 6. So my multiplication factor is 6. It's going to be 6. All right, let's make the transformation. X equals 2u. Y equals 3v. So put 2u here. That becomes 9 times 4u squared, right? 4 times y squared, 9v squared. And what do you know? 36u squared plus 36v squared equals 36. Divided by 36, u squared plus v squared equals 1. So by making use of this transformation, the ellipse in the xy plane becomes the unit circle in the uv plane. Okay, maybe I should just write this x, y, right? To integrate over the ellipse, no fun. By means of this transformation, okay, the ellipse becomes a circular region, which is pretty easy to change using polar coordinates. All right, so I'm integrating x squared. X squared is 2u quantity squared. That's a square there. Sorry, but it doesn't look like it. So 2u squared is 4u squared times the Jacobian, 6, dA, the extra multiplication factor, right? So and what I'm doing here is this thing, page 1056. Change x and y to u and v, multiply by the Jacobian, or strictly speaking, absolute value of the Jacobian, and then du dv. All right, so here we are. 4u squared is 4 times 6 is 24, so I took out the 24. U squared is R cosine theta squared. Okay. U is functioning like X, right? V is functioning like Y. So U is R cosine theta squared, dA. And we know dA in polar coordinates is R dr d theta. It's on a unit circle. So theta goes from 0 to 2 pi. R is going from 0 to 1. All right, so that's R squared times R. That's R cubed, right? You know, right here. R cubed cosine squared. R squared times R. R cubed. Okay, integrate with respect to R. Leave cosine squared theta alone. That's R to the 4th over 4. From 0 to 1. Plug in 0, you get 0. Plug in 1, you have 1/4. Take the 1/4 out, 24 times 1/4. And I'm integrating cosine squared of theta. You might recall from your Calc 2, change cosine squared to 1 plus cosine 2 theta over 2 d theta. So that becomes 6. Take out the 2, that's 3 now, right? 24 times 1/4 is 6. Half of that is 3. Integral of 1 d theta is theta. Integral of cosine 2 theta is sine of 2 theta times a half from 0 to 2 pi. And we've seen this theme before. Plug in 0, you get 0. Plug in 2 pi, this becomes 0. You're taking the sine of 4 pi, not 0. So the only thing of substance is this. So 3 times 2 pi. Final answer is 6 pi. And there we go. All right, so I'm done with that section, folks. In fact, I'm done with the chapter. Let me go back and do my focusing thing for 15.9. In case you couldn't see anything there. So there's that. There's that. And there's that. And as far as quiz is concerned on Thursday, I will give you something sort of like this, where you have something in the, say, either the XY plane or the UV plane, and you have to transform it. Tell me what happens in the other plane by means of the transformation. So you get a region, and then by means of the transformation, you end up with something else. Okay. And then there's all that. And yes, these problems, 15 and 17, they can get really long. And I'll have to keep that in mind. So if I have you do an entire problem on the test, either it's quote unquote easy enough to do the whole thing, or I might just have you do a certain portion of it. Like, you know, just show me the transformed region or figure out a Jacobian. And that's basically about it. Okay. All right, so we are finished with everything for chapter 15. So coverage for the next exam is up to here. Right. But again, we're not changing the date, so it's still going to be next Thursday. And so in the meantime, I'll just get going. 16.1 is really not that bad. I'll finish that pretty easily today. So next time I'll go on with 16.2. Not sure about 16.3, and you'll have a quiz. And then Tuesday the 20th, maybe 16.2 or 16.3, but I'll pause the second half to let you ask questions in preparation for the chapter 15 test. And then Thursday the 22nd, all we will do is go straight to the test, nothing else, no questions and answers. So question and answers all have to be on Tuesday the 20th. Okay. All right, so I'm going to start 16.1, our last chapter. So we're almost there, folks. So we're done with what, 12, 13, 14, 15. All we have left is chapter 16. And again, I'm aiming to finish everything by what, Tuesday, May the 11th, so then we can have the last test on the 13th. Okay, so let's see what happens. All right. So chapter 16, vector calculus. Doing a lot of vector work here. All right, 16.1, page 1068, vector fields. Now you may have done some of this in Calc 2. If you took me, we did some vector fields, which are basically slope fields. Okay, see all these little lines here, these marks. Okay, those are like slope fields, or specifically vector fields. Okay, they're trying to show you velocity vector fields of parts of the San Francisco Bay Area, I guess. Okay, so we have something called a vector field now. Page 1069, definition. Okay, let D be a set in R2. It doesn't have to be R2, you can have it R3. As you can probably just guess what happens there. A vector field on R2 is a function capital F bold. And why bold? Because it's a vector. Okay, it assigns each point x, y in D a two-dimensional vector capital F of x, y. So you give me a point, I come back with a vector. So that's different. It's not a point, and then you come back with another point. Okay, so in the xy plane, right, what we're used to is z equals f of y. You give me a point in the xy plane, I come back with a height. Not so here. You give me a point in the xy plane, I come back with a vector. So here's an example. This point, corresponding vector. This point, corresponding vector. This point, corresponding vector, and so on. Okay. Now, of course, it's hard to draw them all because the points would, kind of get in each other's way, so to speak. Yeah. That's why in Calc 2, you may have done this if you did the section on differential equations. You just draw tiny little stubs like this, going in certain directions. Okay. But here, we do want to indicate the magnitude. So the larger the magnitude, the longer the vector. Okay. So in other words, this vector is this long. So I don't want to draw something that's shorter. Okay. So it might have the same direction, but it's a different magnitude. And this is going that way with a smaller magnitude. And this is going that way with a larger magnitude, and so on. Okay. And you can have a three-dimensional case. A vector field in R3. It's exactly the same definition as this, if you look at the wording. A vector field in R3. What's R3? Space, XYZ space. A vector field in R3 is a function capital F that assigns to each point XYZ in E a three-dimensional vector capital F of XYZ. Here's an example. Okay, so you see the XYZ coordinates, and in space, you have all these vectors. Okay, so you're going that way, and that way, and that way, and that way. Give me a point in space, I'm going a particular direction. Okay. So it's a function. It's a weird function. Given a point x comma y, you don't come back with a z, you come back with a vector. Okay, so this point has a vector. This point has a vector. This point has a vector, and so on. That's in 2D. In 3D, in space, okay, maybe this is the point, I don't know, 6 comma 2 comma 3. The vector is that. And maybe this point is 1 comma 2 comma 4. That's the associated vector, and so on. All right, so part of the homework is to graph some of these. So they give you a vector field here, negative yi plus xj. Plot a bunch of points. That's what it looks like. Okay. Somewhat challenging for this one. So even this is not that nice. I mean, ordinarily you say negative yi plus xj, that shouldn't be that bad, but it can get pretty weird. But it almost looks like you're spinning around in a circle. So if you look at perhaps this one, right? Looks like you're going like that and like that and like that and like that. And likewise, if I go over here, you're kind of spinning around like so. So you might have sort of a whirlpool effect, right? It looks like you're spinning in a counterclockwise direction, I guess. And the further away you are from the origin, the bigger the vectors are, as you can see. Right, so that one in tight word, see that circle of radius 1? I can't point it out to you because I'm holding up the book, but those are smaller vectors. Okay, but when you go further away, right? See where it says capital F of 2, 2? It's a much bigger vector. And F of 0, 3, it's a bigger vector. It looks like you're going directly to the left, and so on. Okay, so the first few problems just involve that. It's not really that big a deal, I don't think. Just for fun, here's what some of them look like. 1070, negative yx figure 6. Yeah, it looks like you got spinning around in circles like that. These were obviously computer generated. Okay, capital F of xy is y sine x. It's kind of squiggling up and down, kind of like a sine function would. Here's a weird one. ln 1 plus y squared, ln 1 plus x squared. So it kind of looks like it's going like so. If you can imagine fluid flow, right? Flow of water or flow of electrons or flow of air, right? Fluid flow has a lot of this kind of stuff, as you might imagine. Okay, fluid dynamics. And there's some interesting ones in 3D, 1071. You don't have to write this down or anything, but computer generated. So f of xyz is yi plus zj plus xk. So it's got this funny looking thing. Almost looks like some kind of hurricane storm. Okay, and by the way, you can describe storms or sandstorms or flow of wind sometimes with equations like this. This one is y negative 2x. If I use the angle braces notation, so it looks like that. Here's a top view. There's y over zi minus x over zj minus z over 4k. You get that interesting thing. Okay, now, how do they come up with these? You just take a point in space, plug it in. Okay. So for instance, well, if I were to plug in the origin, 0, 0, 0, I get 0. So I get the 0 vector at the origin, right? Let's say I'm at the point, I don't know, what do they have here? 5, how about just say 1, 1, 1? I have 1, 1, 1, you'd have the vector 1, negative 1, 1/4. So at that point, 1, 1, 1, the vector would be whatever I just said, 1, negative 1, 1/4. Okay. Of course, you can describe a vector with a function, and then you can use a computer, of course, computer graphics to show you this is what it looks like. Okay, and of course, people that work in weather, meteorologists, or study wind currents, and again, in physics, you physics people with fluid dynamics, fluid flow, flow of water, flow of electrons, flow of water, anything. You can show it with stuff like this. So this is the 2-dimensional version and the 3-dimensional version, and you'll just be graphing some. Okay. Okay, and a special field is a gradient vector field. We've already seen the gradient before, right? So it's on page 1072. Del F, the upside down triangle, del F, is the partial of F with respect to xi plus the partial of F with respect to yj. I would normally just use the angle braces. 3 dimensions, del F of xyz is fxi plus fyj plus fzk. All right, so it's a gradient vector field. They're showing you a gradient vector field here, which is kind of interesting. Oh, I thought I'd just show you this. Of course, in physics, you have gravity, force of gravity, figure 14. Okay, a gravitational field. So they've got an equation of it. That's generally what it looks like. Okay, so let's say this is the center of the Earth, or the center of whatever, center of the sun, center of Jupiter, whatnot. Okay, and the closer you are to the center, the greater the gravitational force is, right? Okay, so the bigger vectors are closer to the center. Okay. Now, if you go further and further and further away from the Earth, like the astronauts out in space, right? Then you have a much smaller gravitational field, so much so that you get to the point of saying, okay, I don't feel any gravitational pull. So my weight is essentially 0 out in space, right? But as you get closer and closer to the center of the Earth, or the center of any heavenly body, let's say, the center of mass, then the gravitational field gets bigger. Okay, so, and it's always toward the center. So if you're here, it's going that way. If you're here, it's going that way. If you're here, it's going that way. If you're down here, it's going that way, and so on, right? Okay, so wherever you are on Earth, right? So you could be standing anywhere on the Earth, assumingly if you're on the surface of the Earth, it's the same distance away from the center. We could call the center the origin, let's say, center of the Earth. So you'll feel roughly the same gravitational pull anywhere on Earth, but it's always toward the center, right? So we don't fly out into space. The pull of gravity is toward the center. So that's whether you're here or halfway around the world in Australia or in London, it doesn't matter. The pole is down there. If you're down under in Australia, the pole is that way. And if you're in San Francisco, maybe the pole is that way, and so on. It's always inward, right? So I guess theoretically, if you have somebody exactly halfway around the world from you, I think I saw it before, halfway around the world from San Francisco is somewhere in the Indian Ocean. Okay, but suppose you're on a boat there in the Indian Ocean and exactly halfway on the road. I'm standing up right here. They would look at you and say that you're upside down. Of course, we would look at them and say they're upside down. Yeah, but that makes sense, right? Because your gravitational pull is like that. Theirs is going this way, but they're both going toward the center of the Earth. Nobody's flying out into space, so to speak, right? So that's what we have there. All right, so let's actually do some problems. Most of them hopefully aren't too bad. Okay, so page 1073. Do these problems, and then that'll be it for tonight. And this really isn't that bad. Okay, this is not that bad a section. Okay, 16.1, 1 to 9, 21 to 27 is all I had you do. Okay, so page 1073, for those of you who don't have the book and aren't getting it, sketch the vector field. Okay, so you have to sketch some of them. Okay, that's 1 through 9. Okay, and then at the end, we had gradient vector fields, right? 21 to 27. And for 27, I don't have you plot it. You don't have to plot it. CAS stands for computer algebra system, I think. I want you to plot it, but you don't have to plot it. All right, so as usual, I'll do some. And it's only a little bit past 7:30. We'll probably be done before 8, I think. Okay, number 1. This is the easiest one, I think. F of xy is 0.3, negative 0.4. That's a constant vector. It doesn't change no matter where you are. Okay. So that's 0.3 units to the right, 0.4 units down, and that's the same vector no matter where you are in the xy plane. So there it is. I just drew some of them like that. Okay. So that's a pretty easy fluid flow. All the water is going in the same direction. It's all going that way. Or if it's wind, all the wind is going, it's not turning or anything. Or if it's electrons, all the electrons are going this way. All right, so that was a little bit too easy. Okay, number 5 is much harder, but there's a nice thing about it. F of xy is yi plus xj over radical x squared plus y squared. Okay, that looks like it'd be much harder. It is. There's something I want to notice about this. Ignore the denominator. What's the magnitude of this vector? Square root of y squared plus x squared, or square root of x squared plus y squared, right? You find the norm of a vector, norm, length, magnitude, just square root of a squared plus b squared, right? Square root of x squared plus y squared, that's the magnitude of the vector, right? Look at the denominator. So you're dividing the numerator by its magnitude, which means all of these vectors are what kind of vectors? Unit vectors. They're all length 1. All unit vectors. So that means all I have to do is determine the direction. once I get the direction, whether it's that way, that way, that way, that way, that way, I just make it magnitude of 1. Okay, so I just did some representative ones over here. Okay, the origin doesn't work. Okay, and what did I try to show you here was some key points. All right, so let's see if I can show you what I did here. That's 1, 0, right? X is 1, Y is 0. X is 1, Y is 0. The vector is J. How about 0, 1? X is 0, Y is 1. The vector is I. It's like that. This one is -1, 0. -1 here, 0 there. That's negative J, 1 unit down. This is 0, -1. 0, -1. Negative I. That's 1 unit to the left. Now, I went out to -2, 0, 0, -2, 2, 0, and 0, 2. You see something similar happening, but I already know I have unit vectors, right? -2, 0, -2, 0. That's -2J, but I already know it's a unit vector, so it's just -J. So it's the same thing here. That means -3, 0, it'd be -J. All of these will be 1 unit down. Similarly, this is going to be all 1 unit up. 2, 0. X is 2, Y is 0. That's going to be 2J, which means the unit vector is J. So these would all be J. Likewise, that's going to be I, and that's going to be -I. So let me try to show you that one. That is going to be what? 0, 2, 0 here, 2 here, 2I. What's the unit vector in the direction of 2I? I. So all of these up here would go like that. And all of these would be -I. So this is 0, -2, 0, -2, -2I. So again, what is a unit vector in the direction of -2I? -I. Okay, then the other ones I did that were nice were like 1, 1, 2, 2, and so on. Okay, if I put 1 and 1, the vector is 1, 1. So I just have it going like that as a unit vector. And if I have -1, -1, I'm going in the direction of -1, -1, and a unit vector. So all of these are meant to be unit vectors going this direction, unit vectors this one. Okay. And finally over here, if I'm in quadrant 4, that's like 1, -1, right? 1 here, -1. The direction is -I plus J. -I plus J would be like that. Same thing would happen over here. In quadrant 2, if I take -1, 1, -1, 1, that's like I minus J. I minus J is down like that. Same thing would happen over here. Okay, so this is just a rough sketch of what happens in this case. All right, so that's that one. And the only other one I will show you was 9 because it's 3-dimensional. Just mention quickly. 7 is 3-dimensional, but you should be able to get that easily, right? 7, f of x, y, z equals I. That's a constant. So you draw 1 unit in the positive x direction, a whole bunch of places. So 1 unit coming towards you. It's almost like a bunch of darts. You have all these darts coming towards you. Okay, 9, I'll show you, it's 3D. -y, I. -y, I. So first of all, there's no J component, there's no K component. So whatever the graph looks like, it's only going toward you and away from you, not going left and right, not going up and down, only at you or away from you. Right. So see all the arrows? They're either going in the positive or negative I direction. Nothing's going to the left or right or up or down. And it's dependent on -y. Okay, so over here, y is 1, right? Y is 1. So the vectors at y equals 1 are all negative I. So that's 1 unit into the board, as it were, into the paper. Y equals 2, negative 2I. So the vector is twice as long everywhere here. And y equals 3, 1, 2, 3, negative 3I. So that's 3 times as long. Okay. So if y is positive, they're all going into the paper. And the further away you go in y, the bigger the vector is. All right. This is the origin. See over here, this is meant to be y equals negative 1. If I plug in negative 1, I have negative I, which is positive I. So everywhere where y is negative 1, 1 unit out of the paper, 1 unit coming towards you. And negative 2, negative 2I, that's 2I. So the vector is supposed to be twice as long. Answer my guess, the next one is 3 times as long, again coming out. So if y is negative 3, that's to the left, 1, 2, 3. Plug in negative 3, negative 3I, positive 3I. So I drew that vector 3 times as long. So these are going into the paper, 1 unit, 2 units, 3 units. These are coming out of the paper, 1 unit, 2 units, 3 units, and that's that. All right, that's it. All right, so you only had to do 1 through 9. I did 3 out of the 5, and I actually showed you how to do, number 7. So, right, there's really not much more you have to do there. Okay, then we'll be done pretty soon. Just some gradients. It's a review of what we did before. Okay, find the gradient vector. So 2-dimensional, the vector is fx, fy. 3-dimensional, fx, fy, fz. Okay, so 21. f of xy is y, sine of xy. So the gradient, or del f, upside down triangle, f, is a partial of f with respect to x, partial of f with respect to y. Yes, you can put I and j. As you know, I prefer not to. Less writing, the better. Okay, so derivative with respect to x. Y is constant. So y cosine xy times the derivative of xy with respect to x, that's y. So I'm going to have a y squared cosine xy. The partial with respect to y, unfortunately, I have to do the product rule. There's a y here and a y here. Okay, so product rule, first function times derivative of the second. So y times derivative of sine of xy with respect to y is cosine xy. Then by the chain rule, times the derivative of xy with respect to y, that's x. So it's xy cosine xy. Okay, so this is first times the derivative of the second, plus the second sine of xy times the derivative of the first with respect to y, but that's just 1. So you don't have to put it. So there we go. There's my gradient vector. Sometimes written grad, G-R-A-D, but simply just use it upside down triangle. So there's a gradient vector. That's all. 23, it's a 3-dimensional vector. F of x, y, z equals radical x squared plus y squared plus z squared. But it's actually a little bit easier than this one because you see a symmetry, right? X squared plus y squared plus z squared. I mean, they're all functioning the same, x, y, and z, right? So once you find the pattern for what happens with fx, then you just look at it and say, okay, the same thing's going to happen if I differentiate with respect to y and when I differentiate with respect to z. All right, so del f is fx, fy, fz. Of course, treat this as x squared plus y squared plus z squared to the 1/2. So fx, all of them start the same way, right? 1/2 x squared plus y squared plus z squared to the negative 1/2 times the derivative of the inside with respect to x, 2x. Well, now that I got that, you see the pattern, right? This is going to be the same thing, right? Except 2y, derivative with respect to y. Same thing, it's still x squared plus y squared plus z squared to the 1/2 So if I differentiate 1/2 x squared plus y squared plus z squared to negative a half times the derivative of the inside with respect to y, that's 2y. And similarly, same thing, except 2z. Okay, so all that happens is the 1/2 cancels all the 2's. On top, I have x, y, and z, and the bottom is radical x squared plus y squared plus z squared. So there we go. Okay, 1/2 cancels 2, all of them. All three denominators are radical x squared plus y squared plus z squared, and x, y, and z. Okay, 27, and I'm done. And it's not even 8, so I'll be done in a few minutes, folks. Unless anybody has any questions, then we'll just call it a day. And so I can check off 16.1. So we will have completed that. So next time again, I'll start 16.2. I'm not sure if I'll finish it. You'll get a quiz on transformations, a linear transformation. So you have some figure. What is the new figure after I transform it? Okay. And again, we're aiming for the test to be a week from Thursday. Okay. Any of this stuff, of course, won't be on that test. So we're giving you stuff for our final test. Okay, so next time I'll do 16.2. And so in fact, I might as well just mark this off now. So Thursday, the 15th, 16.2, not sure about 16.3, and you have the quiz. So however far I get, I'll pause and we'll take our exam 4 here, and then I'll just keep going. Hopefully I can land where I want to land. Okay. All right, 27, and then we're done. Okay, never mind about graphing it. So f of xy is natural log 1 plus x squared plus 2y squared. Okay, so del f, it's a 2-dimensional gradient, so fx, fy. So partial with respect to x is 1 over x squared plus 2y squared. Then by the chain root times the derivative of the inside with respect to x, 2x. Fy, 1 over 1 plus x squared plus y squared times derivative of the inside with respect to y, 4y. And that's it. And we are done. Okay, so let me do my focus thing for a few seconds. And if anybody has any question, you can either unmute yourself and say it or put it in the chat. Otherwise, we're done for the day. Should go like that. Okay, I might have to move this over a little. Sorry. Sorry, I guess I can't get all this on one sheet unless I lower it a little bit. But I think you can figure it out. And that's that. Okay, any questions, please? Otherwise, we're done. All right, seeing nothing and hearing nothing, we're going to call it a night. Okay, all right, so good night, everybody. We'll see you next time. Okay, bye, everybody.
Thank you.
Thank you.
Thank you very much.
Have a good night.
Thanks. Good night.
Night.